Greetings, welcome. So I'm still getting ready to do another battery test. And it's just a silly, simple setup with just this one coil here and one pickup coil. But I've been looking at different voltages and different wire gauges. And one thing I'll show you real quick is just this relationship. Well, here's a good one where I got it starting off a little bit better. Here at 2 volts. And that's the percentage milliwatts that you got back from your spike. And then it got worse when it was loaded, but you got some back from the pickup, so the total was actually better. So that's 2 volts, 4 volts, 6 volts, 8, and out to 12, and then out to, well, where did I stop there? Okay, 18. That's what I was getting there. I've gotten it to about a bit over 50% back. It's measuring things across a resistor off of the pickup and a resistor off the bridge rectifier coming off of this coil, the drive coil. So I was spinning this one up to, this is thinner gauge, and I went out to 30 volts, and it was doing about 1300 RPMs. And the neat thing is that once you get past about 1000 RPMs, all like the rattling and the noise that the bearing is making, it all seems to go away, and it's just, and nothing rattles. This is just taped down here. It's full of pennies on the inside, and it's just taped down here. But what I'm going to do now is go back to the 24 gauge and see, can we get away with 27 volts with the 24 gauge, which will probably be going like 1700, 1800 RPMs. So I thought that might be kind of fun for people, because I haven't spun this this fast yet. And so we're going to see if it holds together. Now, the other reason I wanted to get this video out is, when I do the battery test, it's going to maybe draw 40 milliamps, and, it's going to be taking like 5-10 hours. So what do I do in the meantime? I read this. This is 548 pages. This is one I wanted to pass along to people, and I don't say this very often. I think this is important theoretical work. Ampere's electrodynamics, and this for a long time was lost until about 20-30 years ago. Was it translated into English? But before that time, it was like he did all this. I'll just read you a few of the excerpts. These were people who were his, either his or around his time, a little bit later, or a bit later in Whittaker's case. But here's Maxwell, Maxwell's equations. The experimental investigation by which Ampere established the laws of the mechanical action between electric currents is one of the most brilliant achievements in science. The whole theory and experiment seems as if it had leaped full-grown and full-armed from the brain of the Newton of electricity. It is perfect in form and unassailable in accuracy, and it is summed up in a formula from which all the phenomena may be deduced, and which must always remain the cardinal formula of electrodynamics. That's pretty strong praise when, Maxwell is like supposedly the guru. Here's Whittaker. He was 1910. I started on his book. It's actually quite readable. Description or Theory of the Luminiferous Ether, or something like that. He has a couple papers which were not very readable. The math was a bit over my head, but those were 2 papers that I know that the scientist Tom Bearden was saying, you read those papers, you read them a second time, you read them a third time until they sink in. So here was Whittaker. Ampere published his collected results in one of the most celebrated memoirs in the history of natural philosophy. So what I'm saying is, while this is running, I'm going to be reading that. I've made it through the first 30 pages. And, there are numerous other, luminaries of science that are saying the same thing. But evidently what happened is he published his results. They were kind of established, and then things just sort of drifted away from what he said, and they got put into a different mathematical framework and a different sort of model from what he was saying. No one ever really, that I saw, like came out and said, oh, he's wrong. It just sort of drifted away from that. And then this got lost. And about 30 years ago, someone finally translated it. It was someone from Brazil translated it, and other people picked up on it. And so now we have the translation of his work. And this is, I made it through the first, as I said, first 20, 30 pages, and I've already learned a lot. And it's the kind of thing where it's a bit complicated, but it's not incomprehensible. So again, I don't often say this, but I think this is an important read. And this is around the era of Faraday. And my take on things is, if you want to understand things at a good level, don't read the textbooks. I mean, you can read the textbooks, but if you're able to, go back and read what the scientists were saying. And oftentimes when you do that, it seems much more straightforward than what's presented in the textbook, and you see why they were going in the directions that they were. Like, just for instance here, I mean, one of the main things, he established that there are forces between two currents that are flowing. And this isn't exactly the same, but the whole sensor I have there is kind of based off of that. But he's working off the basis also of Newton with the gravitational law, with the inverse square law. And he found something a bit more complicated with electrodynamics. The other thing is, you get all kinds of terminology, also in textbooks, and it's just, presented like, you should understand that or whatever. And when you go back and, okay, this was the first time that word was used, like electrodynamics, electrostatics, and you see why they're using it and what they're trying to get at, then it's easier to make sense of many other things. Of course, Ampere is the fellow that the amp is named after, so kind of a big name. And you can search on Ampere's electrodynamics and you'll find this. If I'm able to post hyperlinks in the description, I'll include a link to this document, which is freely available, thankfully, and great information. So we'll back up from that now, and we're going to spin this thing at 27 volts with thicker wire and see whether it flies apart. Or if it doesn't, then what kind of efficiency we might expect when we do the battery test. Now, I'm not looking for over unity. The two things I'm looking for are, one, an improvement from the 35% that we got last time, and two, whether it matches the measurements through a resistor here and a resistor there, or whether it's better or worse. But first, we got to find out whether this holds together. All right, so first I'm just running it here at 4 volts. And we're drawing a little bit less amperage. It's 11 or 11.1. I'm going to call it 11. And the spike is 9.8 instead of 9.6. So instead of 20, we're at 21 here at 4 volts. I have no idea. I'm just moving things around to see where I get the best result there with the resistive load there. I don't know if that's going to be best for battery charging. Let's skip all the intermediate steps. We'll go to 18 and then we'll go to 28 and see if it holds together. So first is 18. It's got a lot of pennies, so it's going to spin up slow. Here it's just kind of spinning up, and you can see the spikes going through the roof. Let's give it a minute. So it's still spinning up, and it's making a lot of noise. And last time that noise kind of went away. So we're climbing there. See what happens. Now, it sounds like it wants to fly apart, but hopefully it'll calm down. All right, here we are at 18 volts, and we're spinning at 1393. Doing 1338 last time, and it's a teeny tiny bit more efficient. So the only thing left to do is to turn it up to 28 volts. You know, 3 9-volt batteries will be at 9.3 to start. 28 volts, and see whether or not it flies apart. I don't know whether this will end well or not. Alright, there's 29 volts. And you know, the other thing is it has to hold together for like 5 hours for the battery test, so hopefully it'll sound alright. Alright, it certainly hasn't calmed down in terms of noise, but I've got it where we're running at 1704. And when we put in all the numbers in terms of amp draw and what we're getting out from the spike, we've gone up from 55 or 51 up to 60% back now from the spike here at 28 volts as opposed to 18. Now I'm going to add the this, which will slow it down, and we'll probably do a bit worse here, but hopefully we'll get more than how much we do worse here, and so this will actually be a little bit higher than 60%. Alright, I loaded it. We slowed down to 1348. I forget, I didn't jot down what we were running at there. We're getting an infinitesimal amount from the pickup coil, like 4%. But what we're getting out from the spike hardly changed. Only went down 0.5%. So we're getting that much back per measuring from resistor to resistor. Let me shut it down and I'll just talk for a minute. So what I'm gonna do, and for the next battery test, I'm just gonna leave this part out. I'm just gonna run it here, and we'll get 61% back, at least per the measurement of the resistor across the bridge rectifier coming off from here. So that's not great, but then again, we did this the first time with the first set of battery tests, and as I said, you know, you have a battery at 9.4, you've got like 3 at 9.5, and you don't get 30% back. Well, actually we got 35% back, sorry. So this should be nearly twice as good. And the main thing I want to do now with the battery test is find out whether, you know, having this across a resistor like that really tells us what we think it tells us. So what I don't want to see when we do the battery test is we end up, you know, again with all these seemingly charged batteries, and it's again like 30 or 35% back. What I'd like to see is like 135% back. Sorry. I would, but it would be nice if it's 60, and if it's a bit more than that, like 70 or 80 or 90, I'll take it, and we go from there. One last thing I'll mention, and then I'll wrap the video up, is right now we're not emphasizing this pickup coil. See how big an air gap there is there. Now what I've seen when I emphasize that, but bringing this in closer, is you get more out of here and you get less out of here. However, when you add the two together, this ends up being about the same. So in other words, you could end up getting like 20% out of here and 40% out of here, and again 60%. Now, what's nice about that is that I can think of maybe a half dozen ways to, like, obviously increase the torque here without greatly affecting the amp draw. And so probably the most obvious would be you take a second coil, drive coil, and put it in series, and you have that now with double the amp turns around another magnet, but half the amp flow. So the amps are cut in half, the amp turns are the same. So technically, if there's not feedback between those two, you have the same motive power and half the amps driving it. Secondly, you could put either bring this up here and put another one up there, or you have another segment of this down beneath there, so you're taking advantage of both this end and this end, and that should also double the torque. Not to go through all of them at you, but thirdly, that the problem with the pulse motor is it pulses and then it's off. So you put a second sensor in, these are spaced 45 degrees apart, so like 15 or, half 40, 22.5 degrees apart, and have another coil there so that it doesn't have, it has half as much time where it's coasting. And that increases the torque, and you're still getting the pulse thing. So now you have two pulse things to place out to two sets of batteries or capacitors. Another one, this one, I'm talking about it and I haven't done it, do a magnetic ramp. I've done that, just like super gluing things on CDs, and it worked beautifully. So now I can 3D print it, and you can do that. That's something that works. And then the question becomes, can you make it really work like the Howard Johnson? What a funny name. Howard Johnson and John Bedini thing, where you don't need any of that anymore. You don't need any of the circuitry. It just spins. So but even before you get to there, you can get significant extra torque from a magnetic ramp. And then it's like Lucy and Charlie Brown with the football. The magnetic ramp comes in all the way there, and then boom, you switch the magnet on. So you get all of the magnetic ramp, and boom. Other people refer to it as a V-gate, and you actually could set it up as a V-gate on here, but I'd probably just set it up as a magnetic ramp. So all that needs to be looked at. Probably the very first thing that I'm going to look at is the spacing of the magnets on here. So in other words, I have about one magnet here, 45 degrees, one there. There's 6 of them. And what I want to determine is whether the spacing of these magnets is interacting with the spike. And or, if not, then that's great. So print one with 4, and perhaps the spike will do better, because I'm seeing, the best spike in terms of input from this all the way out here. But again, I'm just kind of going at things empirically. So that's worth doing, is 1, 2, 3, 4, and see what happens with the spike and whether it improves. If it stays the same, then instead of 6, you have 8, and you bring it in closer, and that means that right now you're getting a push-pull, and you're getting a push-pull from like there and there. If you're getting a push-pull from there and there, it's going to be a stronger push-pull. And then the final question, now what I kind of suspect is that the spike will improve with 4, but I don't know that. And I'm hoping that it doesn't, because then you can bring these in, and that gives you more torque. And then you finally have the question of, what if you just north magnet, south magnet right up against it? and maybe you make the coil a little bit smaller. But would that work? Because there'd be a lot of cool benefits to it if it did work. And of course, lastly, there's the issue of adding more mass. I've just got pennies in here. You just have to make sure that the rotor's not wobbling and not imbalanced. Because if you have a bit of wobble and you start adding mass, it amplifies that resistance from the wobble so much that you don't get any benefit from the added mass. But with this one, it spins faster, as was demonstrated, both unloaded and under load with the extra pennies in. So I don't know if the magnet spacing is going to be all that exciting to people. Maybe we should go to like 200 volts. But that's what I'm most curious about. And the one that I really want to do, that I don't want to put off forever, is the magnetic ramp. I want to do that really soon, like this fall, and hopefully in a few weeks. Zoop over there. That'll be darn cool. In my eyes. All right, thanks for coming along, and stay healthy and keep smiling, everyone. Bye-bye.